All right, so let's see, let's go to Moodle for a second. There's only one last piece of unfinished business. By the way, if you checked your Moodle accounts, I did put in the grades for the second midterm. They're in there right now as we speak. And if you don't see anything, let me know. As you know, emails are not reliable, and it's possible you've sent me something that never arrived. So just take a look, and if it's blank, then go ahead and get in touch with me because that means something went wrong. But for the most part, they're all, I mean, the rest, the ones I got are all in there. Let's put it that way. Right. The ones that somehow may have gotten lost in hyperspace, well, those you'll have to resend me. But once you do, I'll immediately take care of them. Okay. So anyway, so all that's left to be done besides that is the sample final. Okay, so it's down here somewhere. And of course, this is exclusively, oh, by the way, the final is right there. You can download it anytime you want and start working on it. So the sample finals here is based exclusively on chapters 11 and 12. So let's get that going. Okay, and let's see, was there something? Yes, I had already posted an announcement about the due date of this final exam. Now, we're ahead, obviously we're ahead of the game. Normally, if we'd been meeting in person, we would have our final exam in person during the week of the 13th. I believe for us, there it is, the 19th. All right, I think what that means is that it was supposed to happen on Thursday, the 16th, I guess that would be. But because that's the beginning of a weekend, if you really need the extra time, you can send it in as late as Sunday the 19th, although I don't think it's going to take anything like that much time. But you do have a lot of time to finish it. But if it doesn't get here by then, you might end up with an incomplete or no grade at all. So, you know, you want to be careful, but that should be more than enough time. So, yeah, the Thursday that we would have taken the test should have been, let me just double check that. Right, the 17th. That's what I thought. Okay, so in other words, today is the, oh no, this is not the right one. What's going on here? That can't be right. Hold on. Okay, let's try that again. Today is Monday the 6th. Um, the finals week is the week of the 13th. We were supposed to have ours on the 16th, which means the grades are not going to be due till early the following week. So I can give you up until the 19th to get it done. But I strongly encourage you not to wait that long. You know, obviously you don't want to wait until you've forgotten everything, but also you might want to just get it out of the way and get it done as soon as possible. I mean, unless there's a really good reason for waiting that long. And like I said, the test is already sitting there. You can download it even as soon as we're done if you want to. And it's the usual format. You know, send it me my email. Now, what I'm going to do here, though, because it's very important to make sure I get them all. If I see that I haven't received it yet, let's say sometime during the week of the 13th, I might send you an email and just say, have you sent it or not? Because like I said, since we can't be 100% sure that I'll receive it when you send an email, I might just write to you if I don't see it yet and just say, well, have you sent it yet or not? And if you already have and I don't have it, that way you can resend it to me. That way we can take care of this before the deadline. So that's probably what I'll have to do because I've completely lost all of my confidence in technology. It just, you know, you have to assume that it's going to fail at the worst possible moment. And that's what will happen with at least one of you. So I want to make sure that if your test does not get here, that I let you know about it right away. All right. Anyway, so in the meantime, let's do this. And let's see how well you remember everything we did in these two chapters. Here it is. Okay, save it real fast. Um, Oh, and of course, one more thing. As soon as we're done here, I'll post the solutions. All right, so let's do this. All right, so first of all, we have, as usual, our short answer questions. And, these don't, usually they only require a very little bit of writing. Oh, by the way, one more thing. I have to pop out one of my disk drive, external drives so that I can put on my my tablet here. Hold on one second. Oops. Okay, wait a minute. Okay, good. So hold on one second. All right, here we go. Now, what two conditions must be met for events A and B, or any two events, to be independent? All right, so that means if we're assuming that the events are A and B, then you need to show that the probability of A given B equals the probability of A, and the probability of B given A equals the probability of B. Okay, it has to be both. One is not good enough. All right, very good. Now, how about this one? What is the relationship between an event and a sample space? So very simply, an event is a subset of the sample space. That's all it is. Okay, it is included in the sample space. If not, then we cannot calculate its probability. That's why this is so important. Now, for two events to be complements, once again, there's two things that have to be true. So in this case, there's actually two different ways of doing that. You can show that the union of A and B is the entire sample space. And, oh, I just realized there's a chat here. I didn't notice it. Sorry. Oh, okay, good. Thank you for letting me know. And in addition, their intersection is empty. But you can also rewrite it in the following way because it means the same thing. And in some cases, this is the only information that you have. If it turns out that these two conditions are true, then it amounts to the same thing. And in many of the problems that we look at, we go through and calculate all these probabilities, and then at the end, they ask you if they're complements or not. So just remember, if the probability of the union is 1 and the probability of their intersection is 0, then you're good. That means they're complements, but it has to be both. Or you can write it as you saw on the top. And so that's what it means to be complements. And if you want to think of a real world example, we did several of these. For example, the red cards and the black cards in a deck. Why are they complements? Because all the cards have to be either red or black. In other words, the union is the sample space, but there is no card that's both red and black. In other words, their intersection is empty. All right, now here's one. I find that this one sometimes trips people up. If A and B are mutually exclusive, that means that they can't both be true at the same time. And therefore, the probability that both of them will occur is just 0. All right. Like I said before, if you had red and black cards, the probability that a single card is both red and black is 0 because both things can't be true. So the answer is simply 0. That's what it means to be mutually exclusive. They cannot both be true. Therefore, the probability of their intersection is 0. Now, the simplified multiplication rule, you might recall, is used when two events are independent. Okay, so unlike the addition rule, there's a simplified version there too, where we only can use it when the events are mutually exclusive. This is different. The multiplication rule, we have to prove that the events are independent to use the simplified version. All right, well, now here's a simple one because we constantly talk about it. If we pick a single card from a deck, if A is the event that the card is red, then A complement would be the event that the card is black. It's that simple. Because again, all the cards have to be one or the other, but none of them can be both. All right. Now you could easily imagine me changing this up a little bit. If it said instead, I pick a piece off of the chessboard, A is the event that the piece is white, what would be the complement? Well, again, it would be that the piece is black because all the pieces on a chessboard, as you know, are either white or black, and there's no such thing as a piece that's both. It's either one or the other. Oh, here it is, the simplified addition rule. Yes, of course. And by the way, let me just quickly remind you what the simplified versions are. So let me scroll this back up for 1 second. That's this one. It just means that there's no conditional probabilities involved. Okay, we can use that rule when the events are independent only. All right, otherwise we have to use the full version of the multiplication rule. Now, how about this one? The simplified addition rule, that's this one. And this is used when A and B are mutually exclusive. In other words, their intersection is empty. Okay, so in other words, you do not have to take that into account with this rule because the intersection is empty. In other words, the probability is 0. Now, how about this one? Sample in a population. So remember, again, we have this concept of the subset. A sample is a subset. Actually, it's a full sentence. Okay, a sample is a smaller portion of the overall population. And there's many different samples you could draw. For example, the population of New York State could be a subset of the population of the entire country. Okay, so if you're looking at the entire country as the population, the state of New York's population would be a subset or a sample. Okay, so a permutation is a selection of objects where the order of selection matters. A combination is a selection of objects where the order does not matter. And that's really the key difference between the two. They're both cases where we're selecting objects from a group, but the order matters with a permutation and it does not matter with a combination. And we need that information to calculate the actual number of permutations or the number of combinations. Okay. And then finally, how many arrangements can be formed from a set of 5 objects? That would be 5 factorial, which is 5 times 4 times 3 times 2 times, whoops, times 2 times 1, which is 120. Okay, so in general, we can create n factorial objects from n objects. So anytime you see the word arrangements, just be sure to use the factorial operator. All right, now here's a case where we're going to calculate some measures based on the sample that you see above. Now, by the way, don't forget, your job is to make sure that you notice that this is a sample, because if you get that wrong, these last 3 will all be wrong. Okay, so just be aware of that. Now, let's start with the first one. So the mean, sample mean, very straightforward. Actually, let me do one thing here, just so we don't have to keep scrolling back and forth. Now you notice this is the sample mean, designated X bar. The procedure tells us simply to add up these numbers, and in this case, divide by 4. I'm sorry, 6. 6. Okay, so that turns out to be 12 over 6, which is 2. Oops. Now for the median, we need the sorted values. And in fact, we'll need it for a few other cases as well. So the sorted sample is -1, 0, 1, 3, 4, 5. So with that information in place, we no longer need the numbers up here, not really, but the median is this. Now, since we have an even number of observations, we will choose the 2 in the center and then average them out. So that means we're looking at these two. So therefore we have 1 plus 3 over 2 equals 2. All right, now for part C, they're asking us for the mode. And again, we need the sorted values for that, or let's just say it's simpler that way. It's not really necessary, but it's so much easier that way. And remember here, what are we looking for? We're looking for repeated values. And with the understanding that there may not be any. Okay, now you can see here, that's exactly what happened. Since none of the values are repeated, there is no mode. That's it, there just isn't one. There doesn't have to be a mode. Unlike the other measures, there may be no mode, there may be 2 or more modes. We don't know until we look at the data. Now for the range, again, it's probably best to look at the sorted sample, because what we're looking for is the difference between the largest and the smallest elements. The range is the maximum value minus the minimum value, which is 5 minus -1, or 6. All right. Now, the next two are a little bit more, 3 are a little bit more challenging, but not really. The only one that's really tricky is E, the variance. Okay. So first things first, let's remind ourselves that this is the sample variance. So the formula looks like this. And in this case, we already know that X bar is 2. And here, though, we typically use the original data. We don't necessarily need to sort it for this case. So let's plug in some numbers. And with these types of problems, you may run out of space on your paper. Just have to be a little careful. And in the denominator, now remember, n in this case is 6 because there's 6 observations. Of course, that means n minus 1 is 5. So all we've done is gone through all the x's, subtracted the mean in each case of 2. We square the results, add them up, and divide by not 6, but 5. Okay. So that leaves us with okay, and then we can, so I usually like to do it this way in stages rather than trying to do it all in one shot, because that's when you start making mistakes. And it's certainly easy enough to make mistakes with this calculation. Actually, we can jump down now. All right. And so when you add those up, you get 28 over 5 or 5.6. All right, now the variance was part E. Part F is the standard deviation, which is easy because all you have to do now is take the square root. And that's roughly 2.366. All right, now the great thing about this is that we can use two numbers that we've already seen. And that proves to be 118.3%. All right, so as you can see, once you get the variance, the standard deviation and the coefficient variation are very simple. The variance is really the only truly challenging calculation in this section. So, as long as you're careful with it, you really shouldn't have any trouble with it. But also, of course, make sure you notice in the beginning whether this is a sample or a population. Because like I said, if you got it backwards, then your answers to E, F, and G all will have to be wrong. And that hurts to lose all those points because of one mistake. Okay, so now we turn our attention to probability theory again, which is more conceptual and less computational. We're going to flip a coin. Ooh, 3 times. That's a tricky one. So remember, we actually did this once in the class. How do you represent the flipping of a coin 3 times without making any mistakes? Well, you can create the so-called binary tree. You show after one flip, you have a head or a tail. If you start with a head, the next coin can be a head or a tail. If you start with a tail, the next coin can be a head or a tail. And then once you get down here, first, after having 2 consecutive heads, you can get a third head or a tail. Here you can have a tail, a head, tail. And so from each, now you notice the drawing is getting a little messed up, but what I'm hoping that you can see here is how one row flows from the ones before it. Okay, in other words, wherever you are, you've got 2 choices. You can either add a head after that or a tail. So after 2 consecutive heads, you now get either a third head or now the first tail. HT is followed by either an H or a T. TH is followed by either an H or a T. TT is followed by an H or a T. Now, when you do go to put together the sample space, though, I think you're best off writing it in the following way. Now, I'm going to change the sequencing ever so slightly. We'll see what I mean in a second. I would like, whoops, what did I do? What I'd like to do is gather up all the cases with 3 heads and then 2 heads, HHT, HTH. Now, you don't have to do it this way, but I think it'll make things a little easier for you. Then all the cases with 1 H, which are these 3. And then finally, the case with no heads, which is TTT. By putting them in this order, it's usually easier to identify the events. Okay, so here we have the sole case with 3 heads, the 3 cases with 2 heads, the 3 cases with 1 head, and the sole case with no heads. And in my opinion, this makes it easier to organize and determine what the events are. Because if you notice, the event A is at least 1 head turns up. And that means everything except 3 tails. And so therefore, watch how easy this is. It's just all of these. How simple was that? I like that. And that's again, because we wrote the sample space in a very efficient way. Now for B, we have the event that there's at least 2 tails. And that means if you have 2 tails or 3, that means you either have 1 head or none. Okay. So if you look at these very carefully, in fact, you know what I should probably do? Let me write it up here as well. 0 tails, 1 tail, 2 tails, and 3 tails. So therefore, you know that you're looking for these, at least 2 tails. Now, by the way, this is very important because if you mess these up, you cannot possibly get any of the answers right. So it's really important that this part is done correctly. Otherwise, you might as well just go on to the next problem, because you cannot possibly, except by the purest of luck, get the answers right if you do not set up these events correctly. Okay, now how about the probability? By the way, once again, I just want to note here, because the probability of the head equals the probability of the tail, each element in the sample space is equally likely to occur. And because of that, has a probability of 1/8. Okay, why? Because you're taking 1 out of 8. So just keep that in mind while you're doing these calculations. All right. So for A, now remember, A contains 7 elements right there. You can see, in fact, it's all but the 3 T's. So therefore, that implies 7/8. All right, because you can count the number of elements in A over the number of elements in S. Okay, and that's why it has to be 7/8. And that's because they're all equally likely. Based on the same logic with B, it's 4/8, or you can simplify it to 1/2 if you want to, although it's not absolutely necessary. Now the union, what you have to do here is figure out what elements belong to this union. Now you can see, you put these together, this is A, remember, and this is B. Okay. Now the union, now if you notice carefully, A contains all the elements except for the 3 T's, but they are in B. So therefore, A union B gives me back the entire sample space. Okay. That's important. The union is the entire sample space. Okay. And so that implies that the probability is just 1, because all the elements are included in this set, 8 out of 8. So you can write it as 8 out of 8 or just 1. Okay. Now, how about their intersection? Well, let's look at them and see if they have anything in common. Well, they do, but let's just see which elements they have in common. All right, I'm just going to circle them. Let's see, they both have HTT. They both have THT. They have TTH. Okay. And there it is. Now, because of that, the probability is going to be 3 out of 8 or just 3/8. All right, now these are straightforward because these are the rules. We don't have to actually write out what a complement is. We can apply the rule directly because as you recall, this is simply equal to 1 minus the probability of A one-eighth. And then for the B complement, we have the same setup, probability B complement. Now remember, B had a probability of 4/8. So the final answer is 4/8 or 1/2. All right, now these are the conditional probabilities. So here you have to remember that this equals this is the definition of the probability of A given B. The intersection of A and B, you can see it's still up there, 3/8. B is 4/8. So these reduce to 3/4. Okay. All right, now here, the numerator is the same, but the denominator, remember A has a probability of 7/8. Oh, sorry, I wrote the wrong thing here. This was 3/8, sorry, yes. That's still 3/8, yes it is. 3 out of 8 from up here, remember we did this already. And originally we saw that A is 7/8. There it is, yes, we got it. And so that ratio is actually 3/7. Okay. Now, how about this one? Now, these are the conceptual ones. Are A and B mutually exclusive? The answer is no. There's a couple of different ways you can explain that, or 3 really. No. A intersect B is not equal to the empty set. That's one way of explaining it. The probability of A and B is not equal to 0. Another possibility. And you can also simply say that A and B have at least one element in common. Any of those will do the job, okay? So you can pick your favorite one, all right? But yeah, all 3 are not necessary. Now, independence, we mentioned this earlier. We have to show whether both of these conditions are true. All right, well, let's test the first one. The probability of A given B, as you recall, we just calculated a few minutes ago to be 3/4. Well, we already saw that the probability of A is 7/8. So already we can stop right there because these two are not equal. So therefore, A and B are not independent. You notice how we don't even have to bother checking the second condition because the first one has already failed. It has to be both for them to be independent. All right, now what about this one? Complements. So we did talk about this earlier. We have to show whether 2 things are true We can, if we do it in terms of probabilities, this is how we prove it. Now, we saw earlier that the probability of A union B is in fact 1. But here's where it falls apart. The probability of A and B equals, I think it was 3/8, wasn't it? Yeah, 3/8, which clearly is not equal to 0. Okay, so that is the reason right there. So this means that A and B are not complements. Okay, because one of them is true, but that's not good enough. All right, now how about these? So again, you've seen these before. This is a probability table. These are all probabilities because you can see they add up to 1. So the joint probabilities are easy. For example, this first one is F and D, French roast decaf. And you can find it right there. Same thing with R and E, that's simply regular espresso. F is just the total of this column. R is simply the sum of this row. Then it gets a little trickier because we have the compound probabilities, or the more complicated versions. Actually, let me split this up so we can, I have to be able to see that table at all times. Okay, D complement, we can simply use the rule. And the probability D is right here. Great. Now with these unions, now I just want to remind everyone that in this table, I'll just put a note here. The columns are mutually exclusive of each other, since no coffee bean can be of 2 different types. Okay, by the way, the names of these blends come from the beans that are used to grind them, make them. So there's the Guatemala flavor. It probably comes from Guatemala, but that by itself doesn't prove anything. But that means it's a different bean that's being used, which is what distinguishes it from French roast and espresso. So it can't be the case that the same coffee is both French roast and Guatemala, for example. So in addition, the rows are also mutually exclusive of each other, since no coffee can be both decaf and regular. I know at this point in time, they've got coffees that are like not quite as, have less caffeine and things like that, but basically it either has caffeine or it doesn't. Let's put it that way. So that being the case, therefore, we can use the simplified addition rule to compute the probabilities of unions. Okay, so for that reason, this one can be simply written as F plus G F is 0.46, as you can see up there. G is 0.22. Okay, we don't have to subtract the intersection because there isn't one. It's that simple. There can't be a coffee that's both French roast and Guatemala. Anymore, there can be a soda which is both Coke and Pepsi, let's say. Or a vegetable that could be both a pea and a carrot, like they're 2 different things. All right, so based on the same logic, G or E, that means Guatemala plus espresso. So G, remember the total is just here. Okay, and then lastly, these two are conditional probabilities, where again, you have to use the definition. And DNF simply means decaf French roast, which we had in the beginning. And French roast itself is 0.46. And this ratio is approximately equal to 0.3913. Okay, now, then we have this one. Oh, whoops, running out of space here. Equals the probability of R and D, in other words, regular espresso over the probability of espresso. So we have, this is 0.10 right here, R and E. Espresso, the total for espresso is 0.32, and this ratio is 0.3125. All right, so those are done. And then, oh, let's see what happened here. There we go. So these are combinations, permutations, and arrangements. So the first one, these are license plates. So they're going to have 5 letters, okay, out of 26. Now, keep in mind, the license plate A, B, C, D, E, therefore, is different than E, D, C, B, A. So what I'm saying here is that the order in which we select the letters does matter. And that being the case, each license plate is a permutation of those 5 letters chosen from 26. Okay, so therefore, what we need is this formula, NPR, which you recall is n factorial over n minus r factorial, where n is 5, n is 26. And r is 5. Okay, so we're going to have 26 factorial over 26 minus 5 factorial. Now, that looks like a lot of calculations, but it's actually not that bad. I mean, if you put that into your calculator, each individual number is going to be gigantic. Now, remember, in your calculator, you do have this factorial operator. Let me just go get mine open right now. And you'll see that it's in the bottom, it's in the extreme bottom left-hand corner, but make sure you type the number first and then the x factorial. Okay, and then, so you would have 26 x factorial divided by 21 factorial equals, all right, so let's try that. 26 factorial divided by 21 factorial equals, and it turns out to be 7893 600. By the way, notice in this calculator, it has a tiny little fractional part. Don't include that because this has to be an integer. I don't know exactly how that's happening, but something about the way they're calculating scientific notation is causing that. So just leave out any fractional parts that might pop up. Okay, It is approximately 7 million. It is exactly 7,893,600. All right. So that's a lot of plates with just the 5 letters of the alphabet. But of course, that's not nearly enough for the United States. So that's why we have so many letters and numbers. All right. Now, how about this one? A bakery offers a new style layer cake. Customers choose 3 flavors out of 6 before they bake the cake. Now here, the order does not matter. They're all going to get mixed into the batter any way you choose them. Chocolate, vanilla, and mint, let's say. You choose those and they go in the cake. And when it comes out, it's just one big cake. There's no distinction between the flavors. Does not matter. So each choice is a combination. Okay, so how do we figure out combinations? N factorial over R factorial. So it's a little bit more involved. That extra R factorial there comes from the fact that it's a combination rather than a permutation. So here, N is 6, R is 3, because we're picking 3 flavors out of 6 that are available. Now 6 factorial is 720, 3 factorial is 6. All right, so you've got 720 out of 36, which is 20. So there's 20 ways of choosing this cake, okay? All right, and then finally we have this one. We have a bookshelf with 3 titles, which you might want to look for on Amazon. Why Everyone Loves Math, The Mathematics of Opera, and Mathematicians Are Cooler Than You. Okay, so let's say you buy these 3 books for your home bookshelf. How many different ways can they be arranged on your bookshelf? Let's say there's only room for 3 books. So you're going to have 3 factorial because you have 3 books. And these are arrangements, by the way, because you're taking all 3 books and just changing the order. Okay, so in the case of permutations and combinations, you're actually choosing from a larger group. But here you're taking all 3 of them. Okay, so that's why it becomes a simple arrangement, which is 3 factorial, which is just 6. And if you're not sure, you could actually write them all out and make sure that you get all of them without duplicating any. Okay, well, that's that. So we're done with the sample final, which means that except for the actual final exam, we're done for the semester. It's hard to believe. It seems like we just started a few weeks ago, doesn't it? But here we are, and we got you through an entire semester of math. And I think we're all better off for it because your math skills are now much better than they were. And you're pretty good at this stuff now. And that can only help you as you go forward into your other classes and into the real world. So hopefully this was a good experience. And if there's no last minute questions, I guess I actually won't be seeing you again unless you're desperate for office hours, which we can arrange a Zoom session if you want it. So don't hesitate to ask if you want to go over something again, not by email, but actually with me talking to you. You can write to me and ask to arrange a Zoom session. If not, if you have something simple to ask, you can send me an email. But in the meantime, all you have to do is fill out your your actual final and have it ready no later than the 19th. And then you can go on to your spring semester after a Christmas break. And who knows where this might lead. All right, so are there any last minute questions? If not, then I hope you have a great Christmas. And you never know when you might show up in another one of my classes. Like I was hinting at it before, I am offering statistics during the winter break if anybody wants more math and you can't get enough of it. Other than that, you never know. It's going to be weird in the spring because we're all going to be back in person again. And if I see you in the hallway and I don't recognize you because your camera wasn't on, you can feel free to come up and tell me that you were in this class because I may not recognize you. Okay. So anyway, all right. So I guess we're done. And so, you get a little extra time today. So maybe you could apply that to your studying. Yes, Kaliak.
I have a question. So will this be posted on Moodle?
Oh, as soon as we're done, I'm going to put this on Moodle.
Oh, and also the video, I missed like the first
Oh, don't
portion.
worry. The video will be ready as soon as it takes a while for it to convert to MP4 form, but it'll be ready certainly later today.
Okay, thank you.
Okay. Anyone else? All right, then I guess, well, all I can do is wish you a Merry Christmas, and I hope I'm sure you're going to do well in this test. It's just as straightforward as it can be. It's exactly what we just got through doing. Yes, thank you, everyone, and have a great break. Yes, I think we deserve it after this semester. And don't forget to check out your grades. I did finally get them into Moodle, so you can go look and see. And they were all very good, by the way. All right, you're absolutely welcome, everyone.
Can I talk to attend the class real quick?
Yes.
Thank you.
Okay. We'll give everybody a minute to
Oh yeah, sounds good.
go home, wherever they are.
Yeah, we can if no one
Yeah,
else.
okay.
Okay, yeah. So I know this is gonna sound very like nitpicky. And I remember I talked to you on the first day about like just like the way you grade it. So you said you do or don't give A pluses, or you did max.
Oh, no, the school has A pluses. If your average is at least 95, you will get an A plus.
Oh, okay, okay. Because I
worry
saw
about
I got one. This sounds so nitpicky and obnoxious, but I saw I got one wrong on the first midterm.
Uh-huh.
I don't know if that brought it down to a regular A.
No.
But okay, cool.
That's not nearly enough. Yeah, no. And in fact, honestly, even if you're close, like 94.4 or something, I usually just round it up. If you're that close, you've got nothing to worry about.
Okay, perfect. That's literally all I say. Yeah.
Okay.
And then I'll keep you posted on the final.
Okay, good.
Any questions I have on it?
All
All right.
right.
Thank you very much. Take
All right.
care.
Okay, bye.
Bye.